Hello everyone, hope you're all doing well. This week's topic is the dynamic shoreline, and I find this to be a pretty interesting part of oceanography because the shoreline is the part of the ocean that's most familiar to most people from going to the beach, things like that. And here in Georgia, of course, we have a dynamic shoreline, and so I think this will be an interesting unit for you. Hope you're all doing well, and we'll go ahead and get started. Before we jump right in, I just want to remind everyone what the word dynamic means. So dynamic means changing. Our shorelines change quite a bit, especially here in Georgia because we have sandy shoreline here as opposed to a rocky shoreline. So our shoreline is changing. It's changing enough that we can see it from season to season and we can see it from year to year, but also it changes on more of a geological scale where it changes over the course of many, many thousands of years. For example, if you think about sea level rise and sea level fall because of climate differences in the ice age, well, 100,000 years ago, when we had an awful lot of the world's water tied up in glaciers, our shoreline was very, very far to the east, like 75 miles to our east, right? So we see change on several different scales, daily, and then seasonally, yearly, and then on big, big, big time scales. One of the most important forces when we talk about the dynamic shoreline is the force of breaking waves. This is really, this is the force that causes the most change in our dynamic shoreline. So I just want to remind you, we've studied waves before, but I want to remind you a little bit about waves. So the first thing you need to know is that breaking waves bring energy to the shoreline, and their energy changes the shoreline. So remember that as waves move towards shore and get into shallower water, wave speed decreases, so the wave slows down. Wave length decreases, so the waves get closer together. Wave height increases, they get taller. All right. Remember that waves refract, okay? And refraction is when waves bend. And this happens because of the friction on the bottom. And when they bend towards shallower areas, okay? So they break typically very parallel to the shore. Even if they come towards shore at an angle, they start to turn towards shore when they actually break, okay? Waves eventually become unstable and break in very, very shallow water. So these are sort of the basics of how waves behave. And some of the information that we want to think about here with the dynamic shoreline is that waves generate a couple of important things. One thing they generate is something called a longshore current. This current flows parallel to the beach, okay? And then we have rip currents that flow perpendicular to the beach. So two different types of currents that occur because of breaking waves. Let's start thinking about beaches specifically. So when we think about beaches, there are several parts to the beach. And so we have the offshore part to the beach, and this is really kind of, the waves might be starting to be affected by the bottom, but it's deeper. They're not starting to break. They're not really starting to change their behavior a lot. But then we get into the actual, what we consider the beach. And so we consider the beach sort of this beginning of where waves start to break, okay? These are our breakers here where waves are slowing down, they're getting closer to one another, getting taller, and eventually breaking, okay? And we call this part of the beach the near shore. So this is sort of where the breaking waves are, on the near shore. And then we have the shore. The shore is this area beyond the breakers, but you know, we have waves swashing up here, right? Washing up and washing back. We call that the swash, okay? So this part that's actively wet quite often is called the foreshore. And then we have this little area here is the backshore. This area might only get wet at very high tides, during spring tides, during storms, things like that. So that's called the backshore. All right, and then quite often our beach is backed by dunes, and often, especially in winter, these look like a cliff. They're wave cut by a cliff. Okay, so this is a typical way we talk about beaches. One thing I want you to notice is that we have all of this stuff going on underneath the waves too. So we have something called a berm. Especially in summer, we have a berm where you have sort of a shelf of sand that gets pushed up by waves. All right, so this is a berm. You can see how it's coming up a little bit, right? And then we also have, very typically, we have a trough here and a bar here, and these are called longshore because they run along the shore. They run parallel to the shore. Okay, so when we talk about waves, we talk about the breaker zone here. The surf zone is just inside of it, and then the swash zone in here. All right, so those are some words we might be using during this lecture. So now that we've talked about waves and beaches, let's work on some new concepts. And one of the really important concepts when we talk about beaches is something called longshore drift. Okay, so we're going to look at this animation here of how longshore drift works, and then we'll talk about it a bit. Let's replay this from about here. One thing that I want you to notice is that these waves are refracting. They're bending as they get closer to the beach, so they're breaking almost perpendicular. And I also want you to notice that the direction of the longshore drift here, of that piece of sand, is going in the direction that they are bending, okay? So this longshore drift, this zigzag, is pretty typical. And longshore drift is an important force in how sandy beaches change. Okay, so we have waves coming into shore. They're bending towards shore, but as they bend towards shore, they're moving sand so that it is zigzagging up at an angle, and then it's coming back straight down, up at an angle, back straight down, and it's moving along the beach. You can almost consider longshore drift as the force behind what we would call a river of sand. So sand moves. It's moved by wind, it's moved by waves, and so sand becomes like a force of it in and of itself. It moves on its own because of these two forces, and it's a river of sand. So it can change the shape of sandy beaches. And one of the things that's very typical is once you get sort of to the end of a shoreline here, see how it's changing direction, this sand keeps getting pushed and starts to build up here, and we get something called a spit. Okay, so this spit will grow out in the direction of the longshore current and of longshore drift, and quite often what will happen is you will start, because water is calm back here, you'll start to form things like salt marshes. You'll have more sedimentation in here. And so you can have this island then grow, or shoreline, whatever this is, grow in this direction because these longshore currents make these spits. So let's see an example of this. This is Cape Lookout. It is in North Carolina. This is a barrier island here called Core Banks. And this is a barrier island here called Shackelford Bank. And you can see there's little inlets here and an inlet here. This is Beaufort Inlet. This is the mainland. This is Beaufort, North Carolina. Okay, and we have Morehead City over here. All right. And these are part of what's called the southern outer banks. This is over here. This is so these islands you can only get to by boat. This one and this one, but this island you can get to by a bridge. And Atlantic Beach is there. Emerald Isle is there. Really nice areas. A lot of people vacation in this area. So let's go ahead and see how this looks. What I want you to look at is this point right here. Okay, so the longshore current is coming in this direction. That means longshore drift is coming in this direction. Here we go. So this runs from 1984 until 2018, and you can see that we have growth in this spit right here. So that's an example of how longshore drift is causing a spit to grow. Now, let's look at an example that is closer to home. So this is in coastal Georgia. This is Sapelo Island here. This is a little inlet, so the ocean is here, and inlet. This is all salt marsh back here. So the town of Darien is like right over here, okay? And a couple of places I want you to watch. The southern end of the island, okay? But I also want you to watch, so this is part of Sapelo Island here, but this right here is actually a little separate island. This is all salt marsh in here, right? And this is an island called Cabretta, and then this is an island called Blackbeard Island, okay? So so we actually have 3 islands that are going on here. And what I want you to watch the bottom part right here, okay? Watch in here, and then watch up here, all right? The longshore current is coming from north to south. That means that sand, that river of sand, is being carried from north to south. And here we go. One thing you'll notice is that the bottom of the island is growing here. And then you'll also notice, especially right here, we see a lot of change occurring right here. See how this is growing out and this is shrinking, all right? So the sand that is up here is moving down here, and the sand that is here is moving down as well. Okay, let's just restart this. There we go. So this is a typical thing that happens when we have these spits grow. We see the path of tidal inlets also changing. Our next example is a little bit closer to home, and it is looking at what has happened in Sea Island when they have built this man-made groin here. So let's just look at this. Let's look at this from above here. So this is the causeway that runs over from Brunswick to St. Simon's Island. So this is St. Simon's. This is the jetty. That's where the village is. You've probably been there. And this is Coast Guard Beach right here. So if you've been to the beach, that's probably the beach you've gone to. This is Gould's Inlet. Okay. But what we're really looking at here is 2 islands, because we have here Sea Island, and this is the very exclusive, very expensive resort. All right, and in the 1990s, the early 1990s, Sea Island was concerned about this spit of land here because they wanted to build out here, but they were losing beach. So they decided, hey, let's build a groin. Okay, so groins look like this. This is the groin that they built at Sea Island. It's a man-made, basically hard wall. You've probably seen these. They're quite often built of rocks, okay? And you can actually kind of see already just from this picture the difference between this beach and this beach. So let's look and see what this looks like here. And so they built this groin in 1992. So pretty early on in the cycle here, you'll see right about here, you will see a little groin pop out, and then we'll start to see changes in the beaches. Here we go. There's the groin, and then watch what's happening right here to this. Now we can compare this to what we saw in Blackbeard Island in our previous animation, where Blackbeard Island was actually growing down. It was growing from north to south. This is actually just disappearing. All right. So you can imagine that that if you have land here, you're a little bit concerned with what's happening because of what happened here. So let's talk a little bit about what's happening with this groin. All right. So we have a longshore current coming from the north, which is here, to the south, and is carrying sand with it because of longshore drift, right? Now, typically that sand would get carried from here to the south, to the south, to the south, and would just feed this beach. But when you build a man-made groin, that sand moves to the south, to the south, to the south, to the south, and gets captured. So this is saving its sand. It's not giving it sand over here. So we're starving this area of sand. This typically would be fed from this area. So you can imagine that if you have property here, well, you're happy about that groin because your beach is, look, it looks pretty good. But imagine that you have property here, or you have property down here, right? So these guys are holding on to their sand, and they're not letting it move down onto this or down here. And so quite often when you build groins, you might be saving the beach in one place, but there's a cost to it here. So those are 3 examples of how longshore drift occurs on our coast. The next type of current that I want to talk about is rip currents. Some people call them rip tides, but it's not a tide, it's really a current. And you can see from this picture here that we have breakers here and we have breakers here, but no breakers here. And this is what rip currents often look like, okay, where you just have sort of a change in the structure of waves. So what's happening in a rip current? So a rip current is found where you have water being pushed in from one direction and pushed in from the other direction, and it needs to go someplace. So typically, if you have this entire thing was all steady with the same size breaker coming from the same direction, that water would come up and it would just eventually have to force its way back through the surf. But sometimes you have differences in the size of breakers because the bottom is different, right? You might have shallows here and shallows here, but it's deeper here, or you might have the opposite or something like that. So you might have breakers that are occurring here that are larger and larger and then much smaller here. So that would encourage this water to find the path of least resistance and all get funneled out in one way. You also might just have slight differences in currents in the way that these waves are approaching because of diffraction, right? So when that happens, that's another way that we end up with rip currents. So these can move really, really fast, and they're too strong for most people to swim against. So if you get caught in this rip current, you can get dragged out to sea. And this is one of the things that lifeguards are always looking for. They're looking for rip currents to prevent people from getting caught in them, okay? Now, one of the things that you want to do if you are caught in a rip current is you don't want to try to swim towards shore. You want to swim parallel to shore so you can get out of that rip current. So we're just going to take a look at a video that shows us a little bit about rip currents here. And I'm just going to I'm going to stop for a moment here before I start it to point out. So this is a fluorescent dye. It's called fluorescein, and they have put this in the beach to show you where this rip current is. So you can actually, they've released it here, and it's being fed out through this rip current here. And you can see that the waves break differently. That's pretty typical. So let's go ahead and take a look at this.
You might have heard them referred to as undertow or riptides, but these ocean phenomena are actually rip currents. Rip currents are narrow currents in the surf zone that move quickly away from shore. A typical rip current ranges from 50 to 100 feet wide and can extend 100 yards or more offshore. It can reach speeds of over 5 miles per hour. That's faster than an Olympic swimmer. That makes them dangerous and potentially deadly, and scientists want to learn more about them so we can better forecast when and where they will form and keep beachgoers safe. Here's what we know. Waves don't have to be huge for a rip current to form. 2 or 3 feet are all it takes. And the weather doesn't have to be bad for a rip current to emerge. They often occur in the nice days after a storm. They're usually strongest near low tide, but can form at any time. Rip currents often form where sandbars are near the shore. They occur at breaks or channels in the bar. They're often difficult to see, but you can spot them in areas where waves aren't breaking, or where there's foam, seaweed, or discolored water being pulled offshore. It's easier to see a rip current from higher up, such as from the beach access over dunes or a lifeguard's tower. Rip currents are a hazard for beachgoers, but by knowing the dangers and what to look for, you can avoid being caught in the grip of the rip.
All right, so those are two important types of currents that are caused by breaking waves coming ashore. All right, so we're going to talk a little bit about the swash zone. And the swash zone is that area above the breakers, above the where the water is where you have surf. And it's just this kind of little area where water kind of has a thin layer, comes in and goes out. And it's very, very important biologically. And one of the reasons it's important is because it tends to be lower energy than where the breakers are. But it's regularly moist. There's a lot of food coming in and out of here. So this is being fed with diatoms and dinoflagellates, all that plankton, all that good stuff, right? So you tend to have a lot of things living here. So one example are these birds. These are shorebirds. We have a lot of shorebirds migrating through our area right now, in fact. But what they're feeding on all sorts of things. Like there's amphipods, which are sort of like tiny little shrimp. Amphipods, isopods, little guys like that. There's also a lot of worms that live in this area, and these worms are filter feeders. But these birds, not these guys specifically, but many types of birds will try to feed on those worms.
At first glance, the habitat appears to be rather uniform, but the multitude of shapes, sizes, bill types, behaviors reveals a much more complex picture. Different species forage in favored microhabitats, and they use the unique tools they possess to harvest particular sizes of prey and types of prey. One bird that really stands out is our largest shorebird, the long-billed curlew. They have this incredibly long, decurved bill, and they're able to reach things deeper in the sand than any other species. You'll see them walking along, and sometimes they'll run forward because they've spotted a crab or something that's darted down into its burrow, and they'll take this long bill, shove it down into this hole, and start feeling around with a sensitive tip of the bill to find the prey item. They're adapted to reaching these burrow-dwelling animals that tend to live farther down in the sand, like certain species of crabs and shrimp, and they find most of them by foraging in the higher tidal areas where the substrate is drier and firmer. Marbled godwits are these tall, graceful shorebirds. They can live to be 30 years old. They're usually in these small flocks foraging in shallow water, and they're usually following a receding tide. And what they're doing is using this long, slightly upcurved bill, and they're more of a tactile forager. They put their very sensitive bill into the sand repeatedly in areas where they have a high probability of locating the food items that they're after, which include small bivalves like clams and types of marine worms. The ruddy turnstone is a really interesting bird to watch. They're very opportunistic in the way that they feed, and they have a lot of foraging methods. Their body and all of its components are really put together in a way that gives them a lot of leverage and strength for pushing things around, for walking, for clambering over things on the beach. They've got this stocky, stout little body and these short, very powerful legs and feet. They've got a short, strong bill, and they use these attributes basically to muscle things around. They're out there flipping over shells, pulling through seaweed, pushing with their body and digging things up and finding little crustaceans and other small invertebrates to feed on.
So our beaches change on a seasonal basis, on a predictable seasonal basis. And so we have seasonal variation in beaches. This shows a typical profile for a summer beach versus a winter beach. So typically in the summer, both of these beaches have dunes, right? So this is the same beach, and so this is where the dune might be. And in summer, what we typically see is a berm that builds up here, and then we have a gentle slope down to the water. So this berm is built. Think about the ocean in summer versus the ocean in winter. We have a lot more storms during winter, so we have a lot more energy coming from waves. So in summer, when we have just gentle waves, those waves actually will push sand up onto the beach, and it will build this berm, okay, which is kind of like a plateau or a step, okay? But in winter, we have much stronger storms. We have them more often than we have them in summer. And so what happens is there's so much energy that is being brought to the beach by waves that water actually carries the sand away rather than carrying it in. So this is the profile of what we would see in summer. This berm gets eroded, and it actually, the water carries the sand from the berm out to a bar. So we see a stronger bar in winter out here, stronger longshore bar, and we see less of a berm. Often water comes straight up to the dune, and you'll notice that this is all of this sand disappears, so the beach is actually lower than it was in summer. So that water can reach straight up to the dune. Quite often we have damage to the dune because of that, so we have dune erosion. So this is a typical pattern that we see in beaches around the world. And I'm going to show you an example of what this looks like right here from the United States. So we're looking at a beach that is on Long Island. So here's New York City, okay, New Jersey, Connecticut, and here's Long Island. And this is called Fire Island right here. And we see here's more of a close-up of it. So it's a barrier island. And this area was really pummeled by Superstorm Sandy in 2012. So this was October of 2012, right? Superstorm Sandy came up the East Coast. It was quite late in the season. It was actually Halloween. And it came ashore in New Jersey. It came ashore like right around here, okay? And so we had winds pushing in this direction. And so this whole area was really pummeled by surf. We had terrible flooding in New York. We actually saw some video of this and pictures of this earlier in the class. So Superstorm Sandy was an important storm. And so we're going to look at what happened to the beaches here on Fire Island. So first of all, parts of the island that were developed, because there's sort of vacation community out there. There's a lot of kind of weekend homes out there, things like that. The areas that were developed, this is some of the things that happened to those buildings and the roads. You can see water came up, destroyed this road, destroyed these buildings, knocked them off their foundation. There's one, looks like there's a couple buildings that are okay, but these buildings certainly would need to be knocked down, and probably I would think twice about rebuilding them, because if we get another storm there, we're in trouble, right? So there was a lot of damage to property out there. Let's look at the changes in the island, though. So this is before the storm, and you can see there's a sandy beach here. We have dunes all through here, and we can see these little like intrusions here. These are places where strong waves have pushed sand into the dunes and over the dune vegetation. These are called overwashes, and there's some of them here. Okay. Now let's look at what happened after the storm. So this is in 2010. This is the week after the storm, November 4th. And so you can see that the beach is much smaller. You can see that we have these huge spaces of overwash. So these waves actually picked up sand and pushed it. There's so many waves pushing repeatedly, push this sand up and over the dunes. So we have some huge overwash here. And then also look at this. This area had so much overwash that it actually broke through, right? So we have a new inlet that has been formed here because of Superstorm Sandy. So what did the beaches look like before the storm? Well, luckily we had a good amount of warning that this took place, because we have such good weather forecasting nowadays in this country. So we had a lot of warning that this was coming. And so some geologists were very interested in what would happen to the beaches from Superstorm Sandy. So they went out and they took beach profiles at all of these sites, okay? And they actually use something called LiDAR, which you fly a plane over the area you're interested in, and it has a radar that faces down towards the ground, and that radar measures elevations. So they use LiDAR to map beach profiles all along here, and this is one. So this is the one we're looking at right here. And this is what the beach profile looked like. So a beach profile basically gives you the shape of a beach. And so they would have some sort of marker here, okay? And we're going to look at beach profiles. They took them for all of these dates. They flew over it for all of these dates. So they have some sort of marker here that they start from, and that marker is something that is reliable from profile to profile, okay? Something that doesn't move. So so this is distance from that marker, and that this is sort of horizontal distance, okay? And then we have this here, this is elevation. So 0 would be sea level, all right? So this is below sea level, and this is above sea level. And one thing I want you to notice is this is MHW, and this stands for mean high water. So this is the average high tide. So they don't have very big tides there. You can see this is 0 and this is 1 meter. So their tide, maybe, you know, a couple feet of tide there, really different from here in Georgia. All right, so that means that I can see sort of the shape of this. So from this reliable marker, I can see what the shape of the beach looks like. So this is on the 28th of October. So this is just a couple days before the storm that they took this. And you can see that we have sort of a dune back here, and then we have a berm. This is typical for summer, that then goes down into the water. Okay, and this is depending on when they flew, they had to stop taking data here because probably there was too much water for them to know anything beyond this. Okay, so it might have been high tide when they flew. All right, so this is what it looked like in late October, and this is very typical for a summer beach. Okay, but then we had the first winter storm arrive, and it was a big winter storm, which was Hurricane Sandy. And you can see that big changes have occurred. So first of all, the beach dropped down. It became lower. So this is like they lost like 6 feet of sand along the beach. Okay, the berm has been pulled offshore a little bit right here. See that? Right, and we also had these dunes. They were cut away. So this is a dune area here. It was cut away into a cliff, right? So this is a typical thing that we see for winter profiles. So we are able to go from a summer profile to a winter profile just with one storm, all right? And let's see how this changes then over time. So I am showing you here, let's see here, the dark blue. This is the day before the storm. Purple is a year later, okay, so still a lot lower. The beach is a lot lower. And the berm is still further offshore, okay, so here is the berm before the storm. Here is the berm after the storm, so it's moved maybe 10 meters, so it's just about 30 feet towards the ocean, okay. We still have this steep cut into the dunes, all right, we still have a cliff there. But then this brown right here, this is the most recent one that they did. This is from 2017. So this is October of 2017. And so this is 5 years later. And you can actually see that this blue profile and this brown profile really aren't very different. So over the course of 5 years, we've had the beach rebuilt. We've had this berm come back, and we've had, you can see that the dune has built back up, all right? So this is sort of an interesting case study in how we see changes to beaches because of winter storms versus the nice summer, gentle summer days, and how we also see these patterns repeated from year to year to year. When we talk about beaches, we talk about the balance of inputs and outputs for sand. Okay, so if you have a beach that doesn't change, then it is in what we call steady state. Okay, it means that the inputs and the outputs are perfectly balanced. Let's talk a little bit about what these inputs and outputs are. So we have here inputs. So some of the inputs would be if you have backshore cliffs and there's erosion that's coming from the cliff down onto the sand, that's an input to the beach. We also have input when we have longshore current. Some of this sand is being moved to here, right? So that's an input. And then we also have the input of sediments from rivers. Now, our beaches here are mostly terrigenous sediment. So it's mostly things that have come from the continents. All right, this isn't always true. This is not true at every beach. Think about some of the really white tropical beaches. A lot of those are biogenous, where most of the beach is made of things like shell. But here, most of our sediments are brought in by rivers, okay? So most of what we find on our beach is of terrigenous origin. So that's an input to beaches. We also have outputs though. So if you have sand down here and the wind blows really, really hard, or we have big waves like we saw in Superstorm Sandy, and this sand gets pushed back up into the dune, well, that's an output. We have this sand being carried away by the longshore current, right? So that's an output. And then we have some of this sand that gets dragged offshore, right, to deep water. So that's also an output. When you have input that is greater than output, you end up with a beach that is growing. When you have output that is greater than input, then you have a beach that is shrinking, okay? So that's one of the things to think about as you're thinking about what happens to beaches. So here's an example of inputs versus outputs. And this is on Cape Cod. This is the very, very tip of, well, not the tip of Cape Cod. This is what we call the elbow of Cape Cod, okay? And so this is Chatham, Massachusetts right here. And we have inputs and outputs. So one of the inputs would be things like, here's a little coastal river here. We have all sorts of little coastal rivers along in here, okay? We have longshore current that's moving from north to south. And we're going to see a lot of change that occurs in some of these areas because inputs are different from outputs depending on where you are. So we have, for example, here more input than output, but up here more output than input. All right. So in some places you are losing beach, and in other places you are gaining beach. This is kind of a cool picture of what's happening over the course of about 30 years. All right. Now, one thing I'll just point out, this is called Monomoy. It's full of seals. There's so many seals here, and there's a ton of white sharks as well, eating those seals. If you want to go see white sharks, I recommend visiting Chatham. Thinking on a larger scale, one of the things that happens because of the input and output of sand is we create these things called coastal cells. All right, and these are relatively typical along the coastline. And this is on the coast of California. Santa Barbara is here, Los Angeles, San Diego. All along here we have the input of rivers, okay? We also have canyons that are offshore. And what happens is we have a longshore current that's moving from north to south here. So we have the input of sediment from rivers, okay? We have longshore drift that carries these sediments along the shore until they reach these offshore canyons. So these are canyons that we see on the continental slope. We talked about them, way back like at the beginning of this class, right? So this sediment basically gets carried down these rivers, along these beaches until they reach these canyons, and then they slump down these canyons down into the deeper waters. And so the coast is separated by these canyons into what we call coastal cells. So here is one, here is one, here is one, and here is one. Okay, we have them here on the East Coast as well. And they kind of connect our beach systems to our deeper water systems. So I think we're going to stop here for this lecture. Our next lecture will start with talking about dunes. I'm going to leave you with a little bit of footage of an interesting beach animal that we have here in Georgia. So we have these guys right here on our beaches here in Georgia, and one of the things that you might want to do is visit some of our beaches, and you want to go there at twilight or at night, and you'll see these little ghost crabs. So these guys live up in the dunes or in the high parts of the beach. You'll see burrows there, you'll see their holes, and they come out during the nighttime to protect themselves. They don't want to get eaten by birds, so they come out only at night. And they will go down and forage in the swash zone, and they are scavengers, so they're looking for anything they can get. They're looking for plant matter, they're looking for dead animals, anything at all they can get. And they're kind of interesting, something that you can easily go out and find yourself. They do pinch, so you want to be careful if you try to pick them up, all right? But they're really fascinating and really beautiful animals that are well adapted to live in our beach environment. We'll stop there for this lecture. Make sure that you're answering the questions that are accompanying this on D2L, and our next lecture will be about dunes.